Okay, I'm happy to introduce the second speaker for today, which is Christian Biefel. He did his PhD at Erlangen-Nuremberg University under supervision of Frauke Liers, and he worked a lot on theoretical aspects of robust optimization. And interestingly, he's now working since 2022 at SAP and is working on quantum algorithms. And he's suggested he could show us some interesting connections where maybe robust optimization could work or could fit in here. So I'm very curious. And please, Christian.
Yeah, thank you for the introduction. So for full disclosure, as you just mentioned, I've not worked on robust optimization in several years, but I've worked on quantum optimization, and consequently, there are no real new results in this talk. So the question is, why am I giving this talk at all? Why should you be interested? And there's a simple reason. So the field of quantum computing is dominated by physicists, which, yeah, I know from personal experience, there's several informal surveys. So 40 to 50% of people working on quantum computing are physicists. Then there are many computer scientists, and only 10 to 15% are mathematicians or operations researchers. So basically, the field of quantum computing needs you to work on the interesting open optimization problems. But before we can talk about these problems, I want to give a short but not too short introduction into quantum computing. And I think the introduction by Nannicini, Introduction to Quantum Computing Without the Physics, is a really good entry point if you don't want to deal with the quantum physics, but just want to see how the computation works. So we'll follow that a bit. So on quantum computers, we don't have bits like we have on normal computers, but we have qubits. And the state of a single qubit is a unit vector in C2. So we have two basis states, the 0 state and the 1 state. And the qubit can now be in any linear combination of these basis states. After you run an algorithm, after you run a quantum circuit on a quantum computer, you have to measure your qubits. And when you measure a qubit, with a certain probability, you get 0 or you get 1. So with probability absolute value of alpha squared, you get 0, and with probability absolute value of beta squared, you get 1. So here we map the qubit back to normal bits 0 or 1. Now, if we have more than one qubit, we need to use tensor products to describe the state of our qubits. So if we have two qubits, we have four basis states, the 0, 0 state, the 0, 1 state, the 1, 0 state, and the 1, 1 state. And note that the ordering is just as if you would count in a binary way. And now if you have n qubits, the general state is of dimension 2 to the power of n and can be described by the sum, again with the condition that it has to be a unit state. So the complex factors have to be so the squared absolute value of these factors have to sum up to 1. Now these tensor products have this nice property that if you have two tensor products and multiply them, you can multiply the individual factors instead, which is useful if you want to simulate small quantum circuits. Now we know what qubits are. How can we compute stuff with qubits? For that, we need quantum gates. Quantum gates can be described by unitary matrices. And here are some of the most important gates, which are used very often. So the first one is the Hadamard gate. Then we have the Pauli-Set gate and the CNOT gate. And now if you want to describe a quantum circuit, you usually draw such a diagram. And here we see we start in the 0 states of 3 qubits here. Then we apply this Hadamard gate to the first qubit. Then we apply this controlled CNOT gate to the first and second qubit. Then again, the set gate to the first qubit. and again, a CNOT gate to those two qubits. And here we only write down the qubits, the gates that actually do something. So in theory, you would have to write identity matrix here and here, but we don't do anything on those qubits, so we can just omit that. And in the end of the circuit, as I mentioned earlier, we measure the qubits. So with certain probabilities, we get 0, 1 back for each qubit. Now, on this slide, we have two terms that you might hear a lot when you hear about quantum computing: superposition and entanglement. So as I said, the Hadamard gate is an important gate because if you start in a 0-0 state and apply Hadamard gates on your qubits, you end up in a uniform superposition. So if you start in this 0-0 state, you end up in this state here. And this state can be described by the tensor product of the states of the individual two qubits here. And the according vector looks like this. Now, superposition means independently, you can measure the qubits independently, and you get equal probabilities for every measurement. Now, this changes if you, for example, use the CNOT gate. So if we start in the 0-0 state, apply Hadamard to the first qubit, we get this state. And now if you apply this CNOT gate, which essentially does the following, if the first qubit is 1, then the second qubit will be switched from 0 to 1 or from 1 to 0. And if the first qubit is 0, then the second qubit won't be changed. But by that operation, we get this state here. And here we see we can't divide this entangled state into a tensor product. That means if we measure the first qubit, the second qubit is fixed. So if the measurement of the first qubit gives us a 0, then we know the second qubit is also 0. And if the first qubit is 1, then the second qubit is also 1. And this entanglement makes it difficult for classical computers to simulate quantum circuits. Because whenever we want to apply a quantum gate to such an entangled state, we have to compute the operation on the entire state, which is in the dimension 2 to the power of n. Right, now we know what gates are. How can we now optimize with quantum computers? And in this talk, I want to focus on the adiabatic theorem, which is used for many algorithms and many approaches. So if we have a quantum system, which is in its lowest state energy, lowest energy state, and we change the system slowly enough, then the system will stay in its lowest energy state. To understand this theorem, we need two terms. We need what is a system? A system is described by a Hamiltonian. Hamiltonian is a Hermitian matrix of size 2 to the power of n, which describes this state. So you can imagine this Hamiltonian as kind of the landscape. So if your quantum system is some space and you have a ball which is in the lowest pit, then this Hamiltonian describes the hills and the pits of this scape. And now the energy of this quantum state is just the state times the Hamiltonian times the state. And the lowest energy is achieved for the ground state, which is the eigenstate for the smallest eigenvalue of this Hamiltonian. Right, now with this Hamiltonian, we can use this adiabatic theorem to get some algorithmic approaches to solve optimization problems. The first one is quantum annealing, which is done on special quantum computers, for example, by D-Wave. And here we start in a quantum system for which we know the ground state, so the state with the lowest energy. For example, we start with a Hamiltonian for which we know that the uniform superposition is the ground state. And then we have to construct a cost Hamiltonian, which describes our optimization problem. I will show on the next slide how this is done. So we have this cost Hamiltonian that describes our problem, and then we slowly change our state, our system from the starting Hamiltonian to this cost Hamiltonian. We stay in this lowest energy state, which gives us the optimal solution to the problem, ideally. Now, on universal quantum computers, we usually don't do quantum annealing, but we have other algorithms that use the gates that I described earlier. So, for example, QAOA is such an algorithm. This algorithm kind of approximates the quantum annealing schedule by discretizing it into p layers with angles. And then what we do here, we again start in this superposition, and then we apply this circuit with these gates. So these are unitary matrices here. So we apply these gates, we get a state, we evaluate the state, how good is the state, what's the energy of the state, and then we do a classical loop to optimize the parameters. So this is a hybrid algorithm to optimize these parameters. And more generally, if we don't want to follow this annealing schedule, PQE just uses any parameterized circuit to minimize this energy. Now, the main question is, how do we get this cost Hamiltonian? So on the next slide, we start with some arbitrary integer problem. We focus on integer problems, so continuous variables are difficult for quantum computers, so we stay in a discrete space. So if we have some arbitrary integer problem, two variables, one constraint, first we have to encode the integer variables by binary variables. We use some logarithmic encoding. Then we replace the inequality by an equality using binary slack variables. We get this equality here. And then we add the equality to our objective to obtain a QUBO, a quadratic unconstrained binary optimization problem, which is usually the starting point for many algorithms in the quantum world right now. So we have this QUBO here, and on the next slide, I simplified it a bit. So given a QUBO, we replace the variables by these operators. These are the matrices you already saw before, and the identity matrix of appropriate dimension. And now we replace all these variables by these operators. We obtain this term here. And if we compute this term, if we compute all these tensor products and simplify it, we end up with a diagonal matrix of size 2 to the power of 3, so 8. And now if we look at this diagonal matrix, we see at position 6, we have this lowest value. And this corresponds to the state 1, 0, 1, which gives us the solution 1, 0, 1. And actually, this is the optimal solution to this QUBO with optimal value -4. So this is the most general way to get a cost Hamiltonian, starting with a integer problem. But there are many more different ways and formulations. And one of the most famous papers is Ising formulations of many NP problems by Andrew Lucas. All right. Then let's quickly talk about some physics. So there are different implementations of quantum of qubits. So there are superconducting qubits, trapped ions, neutral atoms, photonic qubits. There are some even more fancy qubits where physicists don't even know if they exist. And they all have advantages and disadvantages. So for some qubits, or for some hardware implementations, you can execute the gates very fast. For others, you have high fidelity, meaning only few errors. Some you have to cool down, some you don't, some you can operate on room temperature. And now I want to talk about this limited connectivity in superconducting qubits, which are used by the biggest players, IBM and Google in the quantum world. And with this, we come to the first problem I want to talk about. So if we have a quantum computer we have physical qubits on some kind of chip, or in some other way, we have physical qubits, and now we have our quantum circuit, which we want to execute on our quantum computer. So what we have to do is we have to map our logical qubits in our quantum circuit to the hardware. And now if we have quantum gates that operate on two qubits, for example, the C0 gate, the corresponding physical qubits have to be adjacent on the hardware. So for example, if we have a C0 gate on qubit 0 and 1, and 0 is here on 0, and the qubit 1 here is mapped to qubit 7 here, for example, then we would have to swap the information in this qubit to 5, execute the C0, and swap back. Because we can only execute those gates on adjacent physical qubits. So this compiling or embedding a circuit into hardware is itself a difficult problem. And I want to state it here more formally. So we have a number of 1 qubit gates. We have measurements on the logical qubits. We have qubits on gates on 2 qubits. And we have this hardware graph. And this hardware graph depends on how the hardware provider built its computer. And then we have errors on the individual qubits, and we have errors on the links. Meaning, sometimes if you measure a qubit, the measurement will just give you a wrong result. And this is one of the biggest problems of quantum computers right now. They're quite noisy. So you will get many errors, and you cannot run your circuit once and get the correct result, but you have to run it many, many times and look at the distribution if you find good solutions in that distribution. So we have these errors. Now the task is to find an embedding, as I showed before, that minimizes these errors. And as I said before, if 2 qubits are not adjacent, but they have a 2 qubit gate, then we have to include these swaps to deal with that. Now, with these change costs, we have a quadratic assignment problem. So we want to assign every logical qubit to a physical qubit, and we end up with this static quadratic assignment problem. And this is a very simplified version of this embedding problem, because usually real compilers reroute dynamically. So they look at your circuit, they look how can you maybe reorder gates and reduce the number of swap gates. But this is a simplified version where we have this static assignment problem. Now, here comes the uncertainty. We have errors, but the problem is error rates drift between calibrations. So usually the hardware providers do 1 calibration per day and tell you the error they measured on certain qubits and links. But these error rates, they may change between calibrations and even between compilation of a circuit and actually running the circuit on the hardware. So there are the first big question is how can we model this error drift? Usually, if 1 qubit goes bad, also the neighboring qubits get worse. So there are some dependencies if those error rates drift. And if we have a full calibration history, maybe we can also model this uncertainty by some probability distributions. Now, one approach to deal with this drift of the error rates would be to do some recourse with extra swap gates. So assume we do some placement of the qubits on the hardware based on the calibration data that we have. Then we see, okay, the error drifts change. We don't want to do the entire embedding again. So what we do is we just use some swap gates in between that kind of swap our qubits around to avoid the bad links. So that would be some kind of 2-stage robust optimization problem for this problem. And And this is quite expensive. So already the nominal problem is very expensive. So maybe there some adaptability might be interesting in this case, where we just pre-compute some swap plans that avoid certain links for which we know that the error might get bad, but don't have to do the whole thing. Now, to the second problem I want to talk about. So as I said earlier, we usually deal with QOs. And in the literature, if we have uncertain QOs, so if your optimization problem is uncertain, usually robust optimization techniques are not used when solving these QOs on quantum computers. What's done in the literature usually is maybe you solve some scenarios, you keep the best solution, which is the best across the uncertainty set, or you solve your nominal QO many times and see if you find so then you get many solutions back by your quantum computer, and then you just rank this pool by robustness. And the question is, if you have some uncertain integer problem with constraint, can you somehow map this to a good QO without losing too much, or at what price, and solve this on a quantum computer? Again, just quickly the notation. We have quadratic problem with some constraints. We have this slack register, and we have these penalty factors. And now let's assume this constraint becomes uncertain or is uncertain. And the easiest uncertainty set I could think of is if we just have interval uncertainty, and we look at box uncertainty. So every entry of this vector might get to its worst value. What happens? We have this robust counterpart, and now this is basic robust optimization, nothing special here. But the interesting thing is, if we now map this back to, so if we now reformulate this back to a QBO, so if we add this to our objective function again, this QBO has exactly the same coupling pattern as the original QBO. So the quantum computer doesn't care if we have this robust version or the nominal version. It shouldn't change much on the quantum computer. Now, if we use, for example, budgeted uncertainty, we use the well-known result by Berzemas at SIM, and we have to solve at most n+1 QBOs. But again, they all have the same structure. If we only have one uncertain row, of course, if we have more than one uncertain row in our constraint matrix, then the number of QBOs we have to solve would grow exponentially. Now the question for this would be, okay, we have n+1 QBOs. Can we somehow exploit the structure? So we only have to do the compilation once because the QBO looks the same, only the numbers change slightly. But can we somehow exploit this? Can we use one solution of one QBO for the solution for another QBO, or can we somehow use superposition to solve more than one QBO at once somehow? And also regarding this reformulation of integer problems, what about other uncertainty sets? Can they be treated as efficiently as well? And what about the other reformulations, for example, from this paper I mentioned earlier? Now to my last slide, because there are some more problems I could think I thought about, but it's also Claude assisted. So obviously I asked AI, can you find me some problems? But they are interesting problems. So the first one is which I also worked on constraint preserving mixers. So for example, in this QAOA, we had this initial Hamiltonian, which uses a superposition, but you can also use other Hamiltonians which encode your constraints. And that's only good for certain constraints. So is it possible to use robust constraints in this framework of constraint preserving mixers? Then, for example, in this QAA, QAA is very sensitive regarding the angles. And we usually prefer angles for which the energy landscape is pretty flat. So where if we just move slightly, it doesn't change too much because it's just imperfect and there's a lot of noise. And then there are some other problems. So for example, in quantum chemistry, there are the coefficients of the Hamiltonian are not exact. They're only measured. Then error mitigation is a big field where we have to deal with this noise, or where we try to deal with this noise. And also, usually we don't only compute stuff on one QPU, but QPUs can be connected, and how is stuff scheduled on these QPUs, again with these drifting error rates. All right, that's from my side. Thank you for your attention.